Okay, hello everyone. My name is Maz Baromi. I am with R&D team at Wolfram Research, leading Wolfram Quantum Initiative. Today, I'll be talking about expanding exponentials in non-commutative algebra. In particular, I'll focus on Zassenhaus, Baker, Campbell, Hausdorff, and Magnus formulas. Operator exponential is one of the big headaches for anybody who is learning, the quantum. Basically in your advanced courses or in your research, one of the biggest headache that you have is how you can take care of some exponential terms. And there are a couple of reasons for that, being a headache. Number one is that metric exponential is always a headache. Okay, it's a non-trivial process. Number two, many operators that we have in quantum, they do not commute. Okay, so that's why we need the algebraic, non-commutative algebraic structure. And then another big headache that we have in quantum, especially when you learn about quantum field theory, is that many operators that you have in quantum, they are in infinite dimensional spaces. Okay, so you cannot have a simple expression such as Pauli operator and then do the calculation numerically. So that's why you need a very nice way of taking care of your algebraic relationship and do the computation for that. As you may know, non-commutative algebraic packages, they have a long history in Mathematica, but very recently, starting from version 14.3, we have building functionalities for non-commutative algebra. What I have done is basically development of three functions to take care of three famous exponential series that we have in quantum. The famous one is Baker, Campbell, Hausdorff, the famous BCH. Then, Zassenhaus, which is in a sense dual of BCH. And last but not least, Magnus series. Magnus series is also almost the same like Dyson series. And this is basically in simple terms, this is the way that we can understand them. So in BCH, we have the multiplication of bunch of exponentials, and then we want to write it down as one single exponential. The main question is that how we should adjust other terms. Keep that in mind, these operators, they do not commute. In Zassenhaus is the opposite. We have basically the one exponential, and then in the exponent we have the summation of a bunch of operators, and then our goal is to separate them, basically disentangle them. I'll through some examples, I'm going to show it to you that idea of disentangling that. And Magnus, very similar to Dyson series, it's basically the story of time evolution. It's usually we have a dynamical equation like this, and we are interested to find our propagator, our evolution operator. Okay, so let's go through some examples. First, I'm going to start with a concept which is called adjoint action. Which is simply a nested commutation. The main benefit of adjoint action is that you can find terms like this in terms of adjoint action. So when you have basically sandwich an operator by an exponential and the inverse of that exponential, that's basically the exponential of your adjoint action. In simple cases like the one we can show that the first term is basically the first commutator, and then after that we have this nested commutation relationships. Keep that in mind, the action between these operators, they can be anything. The previous case was non-commutative multiply. You can make dot, or I don't know, composition, any operation that you can define for your operators. Okay. Now, based on one of the big questions that we have in quantum physics is how we can simplify terms like this, or read it as exponential of adjoint acting on operator, how we can simplify that. Basically this exponential of adjoint, see it as a super operator. Let me show you a couple of examples. I'm going to start with simple bosonic relationships, which tells us our operators they just commute and the computation is equal to 1. This is the famous annihilation and creation operator for photons. And let's take care of this first term. So our first operator is this one. And then we want to basically find like, this term. What we just need to do is a summation of like, those adjoint, actions. And then like, repeatedly in my code, you are going to see that, I'm going to use some functions for simplification, for reduction of like, that non-commutative polynomial that is the result of like, those summations. There has been more improvement, and there are going to be more improvement in these functionalities. I have put like, their definition in the first slide if you want to see, but basically like, it takes the non-commutative polynomial whose algebra is bosonic algebraic relationship, which is simply like, this mathematical relationship. The story of like, everything that I'm going to tell you is always like, you're going to get a series like this. And then like, that series like, can be represented by, a nice formula. I'm not going to discuss like, the smart way of like, given the result, how you can find the formula, for example, like, how to show that this is basically like, the exponential of negative lambda, but I'm going to confirm them. I'm going to verify them. Okay. So I'm sure like find formula. There are a couple of like, interesting functionalities in Mathematica that helps you to take care of that. So that was like, one simple case, okay? Like, when you have annihilation operator, like, sandwich between like, number operators, these are number operators, that's basically like, the result that you get. You cannot do it like, basically keep that in mind, like, this A and A dagger, I'm not assigning any specific value to them, okay? I'm not explicitly like, feeling anything into them. The only thing that I'm doing here is saying, hey, this is the algebraic relationship between them. Another example, like, is the famous, squeeze operator, sandwiching your annihilation operator by your squeeze operator. And then like, here again, like, more complicated, but eventually like, through some algebraic relationships, like, you can come up with this formula, which is a linear combination of creation and annihilation. And that U and V, like, they are hyperbolic, cosine, and sine functionalities. Okay, so let me like, remind you about a couple of things. So whenever we do any of these like, series and trying to find different terms, keep that in mind. Like eventually you're going to get a series. Okay, so that's comment number one. Comment number two, you're going to always have the headache of like, finding the formula representing that series. This is literally what we do, like, in theoretical physics when we are dealing with all those, like, functionalities. And in order to do that repeatedly, like, you will need to use, like, simplifications, like, what I'm doing here. If you don't do that, you're going to get, like, a big function that's going to look ugly. Okay, so it's just like, the typical process that we have. Okay, let's go through, like, the most common and popular, like, formula that we have, which is basically BCH series. So as I said, like, the idea of BCH is that you have different exponential terms, okay, multiplication of exponential, and then you want to write it down as one single exponential. And you're interested to find, like, these terms, okay, what are, like, those Z terms. In case if you want to see an analytical formula, this fancy, like, formula, which is usually called Duyken's formula, that's basically the representation for the case of only two operators. I guess you can see that, like, even for two operators is complicated. Now just, generalize that to many operators. And basically, like, these are the analytical formulas. Look at, like, the first term is simply, like, the commutation. The third term, it contains, like, nested operation, nested commutation, as I told you. And then as you go to higher terms, you see, like, the number of, like, commutation relationships, like, it increases. And of course, like, as you expand that, like, handling that, like, on pen and paper is going to be very challenging. That said, like, one interesting thing about, like, quantum is that, like, many of our operators belong to small Lie algebra. Okay, Hausdorff, like, spatial unitary 2, 101, etc., etc. So it's going to help us to simplify, like, many of, like, those mathematical expressions. So let me just go through a couple of examples. As I said, like, I'm going to use repeatedly bosonic systems because they are very popular. And one thing that I love about, like, these examples is that these operators, like, they are in infinite dimensional vector space. Okay, so, like, basically, like, there is no faithful representation of them in a finite dimensional space. You cannot represent them by a matrix, etc. So Let me start with the simple case. So we have the multiplication of those two exponentials, and we are interested to find that BCH terms. So the second terms, it's gonna look like this. As I said repeatedly, whenever we get a result, we need to simplify that, and that simplification is done based on the algebraic relationships that we have. So in this case, it's the bosonic algebraic relationships, and you see the result in this case for the second term is a C number, is a scalar, which is a good news, meaning that higher terms, again, this is the higher terms, and after simplifications, you see it's 0. So it means in our BCH series, only the second term survives. All other terms they disappear. So basically this exponential multiplication, it becomes the summation of those two operators plus a C number. And all other terms are 0. So this is not an approximation. This is an exact expression. Okay, so that was one simple example. Another example, let me consider, canonical position and momentum operator. This is a very famous example that, that you have to do in your advanced quantum courses. This is just the definition of canonical, position and momentum operator. And, the famous commutation relationships, you can just confirm that the commutation is, as you expected. Keep that in mind, I just define the algebraic relationship between annihilation and creation operator, and automatically any other operation that I'm considering, through my polynomial reduction functionalities, I can basically fulfill any other commutation relationship that I have. Anyhow, as before, let us consider a multiplication of their exponential, and I can find different BCH terms. Like the previous example, this is also the case that the second one is a C number, and of course, higher order terms are going to disappear. So again, we are going to get a simple formula, which is basically the summation of those exponential multiplied by basically an overall phase. Okay, so these are as I said, simple Lie algebra relationships that we have, and that's why our formulas looks relatively simple. Let's make it more complicated. And again, I wish I had these functionalities when I was taking my advanced quantum courses. Believe me, doing that on pen and paper, it's a big headache. So let's see what we have here. There's a famous operators in quantum optics is called displacement operator. It's basically when you have a coherent state, you can move it in your phase space. But anyhow, it has a term like this, and then you want to see what is the result of the action of those two operators. So in this case, the first term is here, and then the second term, the only difference is the magnitude. I just denoted that by beta. And then we look into the second term in BCH series. As before, as I said, because these are the cases that the algebraic relationship is very simple. We get a C number implying that the higher terms are 0, and we get a very clean formula for multiplication of these two displacement operator. Let me skip through a couple of examples and let me show you another case, which is the famous SU2 basically algebra, Lie algebra. It's a very popular group in quantum. The famous Pauli operator satisfies that, and many other angular momentum operator, the same story. And basically the algebraic relationship is just the commutation relationship is with famous Levi-Civita tensor. Okay, so that's how I set up the algebraic relationship between these operators. And then what we can do is this is kind of later on I have other examples. This is the famous Trotter-Suzuki expansion. So here is the story of time evolution. I have the multiplication of these two operators, and I would say, okay, I would like to find an effective Hamiltonian that is up to, I don't know, quadratic terms of my time parameter, or cubic terms, etc. So what we can do is just in this case, by the way, this is the type of headache that you're gonna have whenever you're working with new non-commutative functionalities. What you have to do, you have to specify your variables, you have to specify your scalars. Okay, so these are simply like C numbers, and you have to also specify your algebra. Okay, so you always need to specify those three terms. I know the code that I'm showing you, it's a bit busy, but again, there is no way around that. So here, I'm just getting BCH term up to the second term, and then I'm going to say, hey, simplify that for SU2, assuming that delta t, theta 1, theta 2, and etc. They are my scalars and scalars. And the variables here, I just denote them by J1, J2. It's just common notation. Call it sigma 1, sigma 2. It doesn't matter. Keep that in mind, these are just symbols. Okay, I'm not specifying anything explicit for them. And as you can see, this is the second term, quadratic in delta t. And then you can find higher terms. And if you put them together, their summation, you can say that, okay, Hamiltonian up to the quadratic term for time is going to take this form. This is a very common method being widely used, in quantum computing. That's the famous Trotter-Suzuki exponential for time evolution. All the examples that I have been showing you so far, they were symbolic computation. That said, you can also give explicit expression to your operators. For example, here I'm saying that, hey, this X is practically my Pauli Z operator, and Y is basically jump operators from lower state to higher state. Okay, this is the famous sigma plus. And then I can say, okay, what's the result of the multiplication of these two exponentials? Here you don't need to specify any algebraic relationships, because you have explicit expression for your sorry, for your operators. We just put it in your BCH functionalities, and then you're gonna get your series. As I told you, the story here is that you're gonna get a series, and then you have to ask, okay, what is the the function representing that series? And in this case, this fancy function is a representation of that function. The main reason that I'm showing you this numerical example is this, for simple cases, of course, it's trivial. You can take care of exponential terms when you can do all those calculations. But think about a many-body quantum system whose dimension increases exponentially, such as a Heisenberg chain, when you have, I don't know, more than 20 qubits, which is a very simple quantum system for the sake of quantum computing, and then you want to do this sort of algebraic relationships. Good luck doing that by specifying your matrices explicitly. Okay, let's move on to another example, Zassenhaus example. So remember, BCH was the multiplication of exponential, and then we wanted to merge them together as one single exponential. Zassenhaus is the opposite. We start with one single exponential. In the exponent, we have the summation of operators. Then we want to disentangle them. Okay, we want to write it down as the multiplication of exponential, and then different terms. It's being widely used for matrix exponential and time evolution. And it has lots of interesting feature. Let me just focus on last example, given looking at the time. Let me just being mindful of time. Let me focus on this example. So let's say that I have a simple exponential like this, the usual algebraic relationship CU2. And let's say that I want to see how I can disentangle that, basically a simple decomposition into a different basis. That for any Lie algebra, you have infinite choices for your basis. A very common basis that we use in quantum is Cartan-Weyl basis, which is simply the linear superposition, linear combination of previous operators. Okay, so going from the previous algebra CU2 to this one is just a basis transformation. Okay, so why this is interesting, I wonder if you guys are familiar with the famous Weyl-Norman factorization. This is a very common technique that let's say that you have a propagator which has some functionalities. You want to basically write it down as multiplication of three different or more operators. Okay, this is the famous factorization. This is almost the same Euler matrices that we have for rotation. That's literally the same story. Long story short, like, let me just like, show it to you that if you start with a very simple case, like, look at like, this exponential term, and you would say, okay, I want to see what is like, alpha, beta, and gamma. That is basically like, the operators, like, specifying your algebra after doing some like, simple algebraic relationships. Let me just show you like, the final result. That's the result that you get. So you see like it's really non-trivial expression, but it's very useful because just imagine that like, the cases that you have a special cases that, for example, you can eliminate like, the effect of this exponential, or like, that exponential cancels out with another exponential terms that like, that you have there. Or just imagine like, let's say that like, this matrix is very dense, but like, these are the matrices that are, much more sparse. Okay, so your matrix exponentiation would be like, much easier. And then as the last example, we have Magnus series. This is basically the big headache of time evolution that we have in quantum. Basically, we want to solve like, a dynamical equation like this. And like, and that like, the solution, we want to write it down as an exponential. And this gamma, we want to write it down as a series that should fulfill like, the time order evolution. We have to be very careful, like, for time. And then like, the solution is usually non-trivial. Okay. The way that the Magnus goes after that is that, again, following the Lie algebra of like, your operators, is a nested commutation in a very fancy way, which is basically the terms that you have here. But anyhow, let me just focus on some examples, and through the examples, hopefully, like, we can clarify what's happening here. Look at like, this very simple case. Like, this is a case of like, you can see it as a like, a time dependent, like, laser field interacting with some atom. Okay, this ft like, can be anything, any time dependent functionalities, and a dagger, like, the famous annihilation and creation operator. Okay, so this is basically like, your Hamiltonian. You set your Hamiltonian, and then you can like, look into Magnus terms. Keep that in mind, like, the main difference of Magnus with previous like, series is that in the Magnus you have to do also the time integration. Okay, so you have, one extra headache. Calculating the nested commutator for inside of like, these integrals is almost the same as the previous case. Okay, so you just look into like, different terms. Here I'm just like, getting the second term. You see, like, I guess you already like, can guess what I'm going to tell you next. Like, the second term in the Magnus expansion is a C number, meaning that the higher order terms, they're going to disappear and they're going to be equal to 0. Of course, like, we can confirm that, like, all other cases, like, are 0. So again, in our infinite series, only 2 terms survives. And then we can put them together, like, after some, algebraic relationships, like, eventually our time evolution, given that Hamiltonian, is going to look like, a constant multiplied by this operator. I wonder if you remember this operator. That was a displacement operator that I showed you at the very beginning. Okay. Let me just scroll down here. I'm just going to show you, like, the final result. So the famous so what? So why this is interesting? Like, look at here. Like, I'm obtaining, the propagator in 2 ways. Like, first, I'm just solving that exactly. And then I'm getting that through, like, the first term in the Magnus, the second term, third, and fourth. And then I'm calculating, like, the norm difference between, like, these 2 operators. By, including more and more, like, Magnus terms, as you can see, like, the difference between the 2 becomes, like, practically, like, negligible, meaning that, like, for this simple case, even, like, the first term in the Magnus, like, is kind of like, is good for all practical purposes. This is a big deal for, like, noise handling in quantum systems, okay? Because, like, again, keep that in mind, like, you have a many-body system with lots of operators, and you cannot handle that, like, numerically. It is practically, like, impossible to work in a space of, like, dimension 2 to n multiplied by 2 to n when n is the number of qubits. Okay, so I think like I managed to cover everything that I wanted to tell you. Sorry that I skipped through like many examples, but you have this notebook, and if any feedback like let me know. You can reach out to me via this email address, and I strongly believe like non-commutative new non-commutative functionalities, they have huge potential for quantum applications. This is an area that we are actively working, and hopefully you're going to see more outcomes out of it.